nuclear chemistry and energy. At the end of this lecture, we will be able to distinguish stable and unstable nuclei based on neutron-proton ratio. We will be able to balance the subatomic particles in the nuclear equation. But before going into nuclear reaction, we must have first a recall. So as we've learned from our previous discussions, we all know that atomic nuclei are represented by symbols such as shown. So the atomic number Z will be the number of protons in the nucleus as shown as left subscript. And the mass number A is the number of protons plus the number of neutrons in the nucleus, and it appears as a left superscript. The reactions that we will discuss in this chapter will be represented by nuclear equations. So a nuclear equation, we must take note that it must be balanced with respect to the nuclear charge or atomic number and the nuclear mass or the mass number. As example, we have the reactant are nitrogen 14 nucleus and the neutron, while on the product side we have carbon 14 nucleus and hydrogen nucleus. As we observe, we have atomic numbers. On the reactant side, we have 7 plus 0, so we have 7. While on the product side, we have, in terms of still atomic numbers, we have 6 plus 1. Okay, so we have a total of, or a sum of 7. So on the both side of the equation, or nuclear equation, we have 7 on the reactant side, and we also have 7 on the product side. So let's check the mass number. So on the reactant side, we have 14 plus 1 equals to 15, while on the product side, we have 14 plus 1 as well equals to 15. So the mass number of each side of the nuclear equation is both 15. Nuclear reactions involve changes in the composition of nuclei. These extraordinary processes are often accompanied by the release of tremendous amounts of energy and by transmutations of elements. So in the table shown, we can differentiate a chemical reaction from a nuclear reaction. So the first one is from the nuclear reaction, elements may be converted from one to another. While on the chemical reaction, no new elements can be produced. The second one is particles within the nucleus are involved, while on the chemical reactions, only the electrons participate. Okay, and the third one, on chemical or on nuclear reaction, tremendous amounts of energy are released or absorbed. While on the chemical reaction, we have relative amounts or relatively small amounts of energy are released or absorbed. And the last one, on the nuclear reaction, we have the rate of reaction is not influenced by external factors. While on the chemical reactions, we have, or the rate of reactions depends on factors such as concentration, temperature, catalyst, and pressure. Henry Becquerel discovered radioactive rays or natural radioactivity coming from a uranium compound. Ernst Rutherford's study of these rays showed that atoms of one element may indeed be converted into atoms of other elements by spontaneous nuclear disintegrations. Many years later, it was shown that nuclear reactions initiated by bombardment of nuclei with accelerated subatomic particles or other nuclei can also transform one element into another, accompanied by the release of radiation or induced radioactivity. Beck- Becquerel's discovery led others, other researchers, including Marie and Pierre Curie, to discover and study new radioactive elements. Many radioactive isotopes or radioisotopes now have important medical, agricultural, and industrial uses. The nucleus. From the previous discussions, we described the principal subatomic particles. Recall that the neutrons and protons together constitute the nucleus, with the electrons occupying essentially empty space around the nucleus. From an electrostatic point of view, it is amazing that positively charged protons can be packed so closely together. Since protons have positive charges, we expect it to repel each other. But the strong force that holds the protons and neutrons together in a nucleus is powerful enough to overcome the electrostatic repulsion between the protons, but it can act over only a very short distance. Because neutrons are uncharged, they can contribute to the strong force without adding to the electrostatic repulsion. A lot of neutrons are needed to overcome the mutual repulsion of the protons in a nucleus of high atomic number, which explains why the band of stability curves upward. We have here neutron proton ratio and the nuclear stability. So the term nuclide is used to refer to different atomic forms of all elements, and the term isotope applies only to different forms of the same element. And we have here a table that shows the abundance of naturally occurring nuclides. So with even uh, proton or neutron proton ratio, we have 157 nuclides, while odd even neutron proton ratio, we have 52, and we have even odd neutron proton ratio, we have 50. The last one, we have odd neutron proton ratio, we have 4. We actually have a series of empirical rules for predicting which nuclei is most stable. So we have first the neutron proton ratio, and as shown, there are 264 known stable nuclei which fall within a relatively narrow belt of stability. The color red in the graph or in the figure shows the belt of stability. But we also need to take note that for light elements, when Z or atomic number is less than 20, this ratio is close to 1. As the atomic number increases, the ratio increases. This means that the belt of stability shifts to the higher numbers of neutron. With very heavy isotopes such as lead 82, the stable neutron to proton ratio is about 1.5. We should take note that the maximum neutron to proton ratio is 1.51. Nuclei containing more than 83 protons are unstable. Putting it another way, no element beyond bismuth are or has a stable isotope. All the isotopes of such elements are radioactive. Nuclei with an even number of nucleons, either protons or neutrons, tend to be more stable than those with an odd number of nuclear particles. And lastly, magic numbers. These are certain numbers of protons and neutrons appear to be particularly stable. These are nuclides with a number of protons or a number of neutrons or a sum of two equal to 2, 8, 20, 28, 50, 82, or 126. So let's try to answer some of the examples. Okay. For a pair of nuclei, list which one is more stable. For letter A, we have lithium 6 and we have lithium 9. For letter B, we have lead 204 or astatine 209. So we have here the following strategies. First is let us determine the neutron proton ratio, and second is we need to check the belt of stability. So for letter A, we have here the neutron proton ratio of lithium 6 is 1, while the lithium 9 has a neutron proton ratio of 2. So therefore, the stability of lithium 9 is, or we can conclude that lithium 9 is the unstable one because of its neutron proton ratio is 2, which lies below the belt of stability. And we also take note, or from our previous discussions, we mentioned that light elements, which is the atomic number or Z, less than 20, the ratio of the neutron proton or neutron proton ratio should be close to 1 for it to be stable. Again, in another term, pag ang atomic number ay less than 20, it should be, or the ratio of neutron proton should be close to 1. So technically, for this one, since ang atomic number ng lithium ay 3, so we just need to check its neutron proton ratio. Okay, let's try to answer letter B. So, as indicated in the solution for lead with atomic number 82, okay, whereas for astatine, it has 85. So we can conclude that lead is the more stable element. Why? Because we mentioned earlier, as uh, as one of the empirical rules, nuclei containing more than 83 protons are unstable. So, again, nakikita natin dito yung Z, no, as the number of or the atomic number, which also the number of proton of an element or a nuclei. So, since 85 siya and it's greater than 83, so technically beyond 83, so 84 above, it will be considered as unstable isotope. Okay, so we will now move forward to radioactivity. So unstable isotopes decompose or decay by a process referred to as radioactivity. A few such nuclei occur in nature, accounting for natural radioactivity. Many more can be made or induced artificially by bombarding stable nuclei with high energy particles. The radiation given off may be in the form of, first, beta particles, identical in their properties to electrons. And the second one is alpha particles, which are with uh, with helium with mass number of 4 and atomic number of 2. It carries a charge of 2 positive because the 2 extra nuclear electrons of the helium atom are missing. And the last one is gamma rays. This one consists of high energy radiation. Okay, so let's now study the mode of decay of the particles. Okay, so we have here a naturally occurring radioactive nuclei commonly composed by first the alpha particle emission. So in which an ordinary helium nucleus is given off. For example, is uranium 238. Okay, we have here um 238 as the mass number and 92 as the atomic number. It emits or nagdecompose. It decomposes to, again, our uranium-238 decomposes to helium plus thorium-234. Why is that so? Uh, okay, so we have here 238 as the mass number. So, nag-decompose siya. Helium, makikita natin 4 ang mass number ng helium. So, we just need to subtract 4 from 238. So, therefore, we have 234. And then, 92, nag-emit siya ng alpha particle. So, we just need to uh, subtract 2 protons from 92. So, we will have 90. Okay. And if you can look at the periodic table, an element with a atomic or with an atomic number of 90, we have thorium. Okay, so other example is we have lead 204. Okay, it emits or it decomposes into mercury 200 plus an alpha particle. So same process. So we just need to deduct 4 from 204. So we have here 200 sa Hg or sa mercury. And we just need to deduct 2 from the atomic number of lead. Okay. So we have 80. So from the periodic table, uh, an atomic number of 80 is mercury. Okay, so we have another mode of decay, which is the beta particle emission. This one produces an electron, and it has the symbol of 0, -1 electron. An example of beta emission is shown. So we have here a thorium with a 234 atomic or mass number and 90 atomic number. So it decomposes or it produces electron. Okay, remember that it has no mass, but it has a negative charge. So what we need to do is uh, just copy the mass number of 234, and then for the uh, atomic number, we just need to add 1. So we have 91. So in the periodic table, we have here atomic number 91. So basing. So we will have an element protactinium. Okay. So again, as you noticed, the charge of or the number of electrons or the mass or the atomic number should be balanced both side of the equation. So dito sa reactant we have 90 and sa product side we have atomic number of 90 as well. Okay? And the uh on mass number 234 on the reactant side, while on the product side it has also a 234. Okay. So another example is here. So we have here radium 228. Okay. So it emits a beta particle, same, with no mass, but it has an electron or a negative charge. So what we need to do is just copy the mass number kasi 0 naman yung mass ng beta particle. And we just need to add 1 for the atomic mass. So we have here 89. So if you can check on your periodic table, atomic number 89 is it's actinium. So again, if you can double check the atomic numbers, 88 on the reactant side and on the product side, we also have 88. Same goes with the atomic or the mass number, 228 for the reactant side, and we have 228 again for the product side. So we have here another example. Carbon 14 will yield to nitrogen 14 plus a beta particle. So again, so basically, the product will be nitrogen, okay, with 14 atomic mass and with 7 atomic number. Okay, so balance naman sila. The atomic numbers and the atomic numbers and the mass numbers of each side of the equation, nuclear equation, is balanced. So we have here gamma radiation emission. So it consists of high energy photons. Gamma emission changes neither the mass number nor the atomic number. So we have here an example. So we have here an excited nucleus. So wala siyang it emits gamma radiation, but it will not affect the the mass number nor the atomic number of that nucleus. Okay, another mode of decay is a positron emission. So basically, a positron is identical to an electron, except that it has a charge of +1 rather than -1. So therefore, positron has the symbol of a 1 electron. So same process. We just need to balance the number and atomic number and mass number of each side of the nuclear equation. So what we just need to take note is the charge and the symbol of each particle. So basically, a positron emission results in a decrease by 1 in atomic number and increase by 1 in the number of neutrons with no change in the mass number. So we have here another examples. Okay, so another mode of decay is what we call K electron capture, in which an electron in the innermost energy level, which is n is equal to 1, falls into the nucleus. So it's actually almost the same with beta particle emission. So we have 0, -1 electron. Okay, as shown in the table, we have here common types of radioactive emissions with their characteristics. It includes their identity, mass in atomic mass unit, charge, velocity, and penetration. So let's try to answer some problems. Okay. Uh, Promethium with atomic number of 61 is essentially non-existent in nature. All of its isotopes are radioactive. Write balanced nuclear equations for the decomposition of A, promethium 142 by positron emission, B, promethium 147 by beta emission, and C, promethium 150 by alpha emission. So let's try letter A first. Promethium 142 by positron emission. So we have a solution. So particle emitted, take note, it mentioned that it is positron. No? So we have here 1 electron. So second one is we need to balance the mass and atomic number. So 142, 61 will yield to positron plus same 142 as their mass number Okay. But for the atomic number, we have 60. So 61 dito, 61 dito. So if we check 60 in the periodic table, so in the periodic table, uh, an element with atomic number of 60 is neodymium. So therefore, we have the following, or we have the reaction. Promethium 142 uh, produces, or as it emits positron, okay, it also produced neodymium 142. So let's try to answer letter B. We have promethium 147 by beta emission. So as we recall, beta emission has a negatively charged, or a negative charged particle. Okay, so we have here. So a beta particle has zero uh, mass, but it has negative negative 1 charge. Okay, so second uh, step is to balance the mass and atomic number. So we have here same uh, 147 atomic number, or atomic mass, I should say, mass number. Okay, while the atomic number, so we will have 62. Okay, you just need to add plus 1 here, so 61. So based on the periodic table, an element with an atomic number of 62 is samarium. So therefore, we have this nuclear reaction. All right, so we have last promethium 150, but it's by alpha emission. So we have helium 4. Okay, all right. So particle emitted is alpha, so we have helium. Okay, with uh, atomic number of 2. Okay, so there you go. So 150 minus 4 because of the atomic or the mass number of helium. So we have here 146. So and 61, so atomic number of promethium. Okay, minus 2 because of the atomic number of helium. So we have here 59. So uh, at what is the element which has atomic number of 59? So if we can check on the periodic table, we have praseodymium. It's praseodymium. Okay. So again, so to sum up, okay, as a summary, no, we just need to take note on the particle emitted, and then second one is to balance the atomic and mass number, and then therefore there you go, we have the reaction. So we have here the following applications. Okay. A large number of radioactive nuclei has been used both in industry and in many areas of basic and applied research. So we have your medicine. So radioactive isotopes are commonly used in cancer therapy, usually to eliminate any malignant cells left after surgery. So cobalt 60 is most common or most often used, and it is by gamma rays, and from this source are focused at small areas where cancer is suspected. There are also other, okay, or more commonly radioactive nuclei that is also used for diagnostics, as shown in table 18.2. So we have here carbon 11, okay, for brain scan, sodium 24 for circulatory disorders, phosphorus 32 for detection of eye tumors, iron 59, which is for anemia, gallium 67 for scan for lung tumors and abscesses, selenium 75 for pancreas scan, technetium 99 for imaging of brain, liver, kidneys, and bone marrow, xenon 133 for lung imaging, and thallium 201 for heart disorders. In chemistry, radioactive nuclei are used extensively in chemical analysis. One technique of particular importance is neutron activation analysis. One of application of the neutron activation analysis is in the field of archaeology by measuring the amount of strontium in the bones of prehistoric humans. So basically, it's possible for us to get some idea of their diet. We also have here commercial applications. So, as shown, most smoke alarms use radioactive species, typically americium 241. It is a tiny amount, or a tiny amount of this isotope is placed in a small ionization chamber. So the decay of americium 241 ionizes air molecules within the chamber. So we will now move forward for the rates of decay and half-life. So the rates of all radioactive decays are independent of temperature and they obey first order kinetics. So the equation is rate of decay is equal to rate constant with the concentration of the species. So and we have here another ln initial amount over the final amount is equal to A multiplied by, or A, which is the stoichiometric coefficient, and which is actually always 1 for radioactive decay, multiplied by K, again the rate constant, and T, which is the time. So again, here A represents the amount of decaying nuclide, radionuclide of interest remaining after some time t, and A sub 0 is the amount present at the beginning of the observation, and the variable K is the rate constant, which is different for each radionuclide. So again, uh, we need to take note that K, or rate constant, is different for each radionuclide. So each atom decays independently of the others. So the stoichiometric coefficient A is always 1, again, for radioactive decay. So technically we can drop it from the calculations in this chapter and write the integrated rate equation as ln sub 0 over A sub 0 over A is equal to KT. So we need to take note that because A sub 0 over A is a ratio of A sub 0 and A can represent their molar concentration of a reactant or masses of a reactant, then the rate of radioactive disintegrations follow first order kinetics, so it is proportional to the amount of A present. So we can write or rewrite the integrated rate equation in terms of N. So N is the number of disintegrations per unit time. So we have there the equation. So in nuclear chemistry, the decay rate is usually expressed in half-life, or T 1/2 of the process. This is the amount of time required for the half of the original sample to react. So for a first order process, T 1/2 is given by the equation ln, by the equation T 1/2 is equal to ln 2 over K, or 0.693 over K. So para madali, you just need to memorize T 1/2 for the half-life, T 1/2 is equal to ln 2 over K. So we also have here that because of the way in which rate of decay is often measured and described as activity of a sample, which expresses the number of atoms decaying in unit time. So the first equation above can be written as A is equal to Kn, where A is the activity, K is the first order rate of constant, and N is the number of radioactive nuclei present. So activity can be expressed in terms of the numbers of atoms decaying per second, or becquerel. So 1 becquerel is equal to 1 atom per, or 1 atom per second. So alternatively, activity may be cited in disintegrations per unit per minute, or perhaps most commonly in curies. Or basically 1 Ci, or 1 curie, is equal to 3.7 times 10 raised to 10 atoms per second. Okay, so let's try to answer the example given. We have here the half-life of radium 226 is 1.6 times 10 raised to 3, or 1,600 years, and it's equivalent to 5.05 times 10 raised to 10 seconds. So letter A, we need to calculate for K, or the rate constant in per second. Letter B, what is the activity in curies of a 1 gram sample of radium 226? And letter C, what is the mass in grams of a sample of radium 226 that has an activity of 1.0 times 10 raised to 9 atoms per minute? So again, we have here given half-life, T1 half of 1 times 3 years, or 1,600 years. So it's equivalent to 5.05 times 10 raised to 10 seconds. Again, yung T1 half, or the half-life, is the time where yung species natin ay nahahati sa eksaktong kalahati. For example, we have 1 gram of radium 226. So basically, that radium 226, that 1 gram of radium 226 will be 0.5 grams after 1,600 years. So ganun siya katagal. Alright? Okay, so let's now move forward. Let's now calculate for the rate constant. So our formula for the half-life is T1 half ln 2 over K. Since this is constant, and we already have this, so therefore we have K is equal to ln 2 over half-life. So we have ln 2 over, so yung question ay per second, so we will use this one. So therefore we have a rate constant of 1.37 times 10 raised to negative 11 per second. Okay, let's now try to answer letter B. So we will use A is equal to Kn. No? Pero meron na tayong K kanina. Our K is 1.37 times 10 raised to negative 11 per second. So what we need to calculate for us to solve for the value of A, sa activity, we have to calculate first for the value of N. So we are given 1 gram of radium 226, okay, and we have 226 grams per mole technically. No? So we will use the Avogadro's number for us to compute, no, to get the value of N. So we have your N is equal to 1.00 grams times then this is just a conversion of in 1 mole there are 6.022 times 10 raised to 20 3 atoms. So we have N is 2.66 times 10 raised to 21 atoms. Okay. So, kumpitan natin yung value ng A, no? So we have here this one, the K, 1.37 times 10 raised to negative 11 per second multiplied by these atoms, 0.66 times 10 raised to 21 atoms. So we have 3.64 times 10 raised to 10 atoms per second. So, anong mangyayari? So, we need to convert this into Curies. Kasi ang tanong is, what is the activity in Curies? Okay? So, we have, in 1 Curie, we have 3.7 times 10 raised to 10 atoms per second. So, we have, in Curies, we have a final answer of how many? 0.95985 Curies. So this is the final answer. Okay, so let's now answer letter C. So we still gonna use this formula, no? Pero sa letter C, given na tayo ng activity. So our activity will be 1.00 times 10 raised to 9 atoms per minute. And the question is, what is the mass in grams of a sample? No, baliktad naman. Kanina given yung mass natin, ngayon ang given is our activity. So, since meron tayong A, meron na tayong K, so we will look for the value of N. So, therefore, N is equal to A over K. So, we have here 1.00 times 10 raised to 9 per minute. Take note, minute expressed siya as minute. So, what we need to do is express this one in terms of second kasi yung ating K value is expressed in per second. Okay? So, in 1 minute, there are 60 seconds. So, ang value ng K natin kanina is 1.37 times 10 raised to negative 11. Okay? Cancel, 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 cancel. So, we have N. It will be 1.22 times 10 raised to 18 atoms. So from there, we will be able to compute for the mass using, again, the Avogadro's number. Okay. So we have here the mass. Okay. So 226 grams. So we have 6.02 times 10 raised to 23 atoms. So our mass will be 4.58 times 10 raised to negative 4 grams. Okay, so we can also compute for the age of an organic material. So we're gonna use carbon 14. Okay, so basically carbon 14 is produced in the atmosphere by the interaction of neutrons from cosmic radiation with ordinary nitrogen atoms. So as nuclear uh, equation shown. So ayun. So basically, it is nitrogen 14 plus a neutron. So it will produce uh, hydrogen and carbon 14. It decomposes into hydrogen and carbon 14. So when a plant or animal dies, the intake of radioactive carbon stops. So consequently, the radioactive decay of carbon 14 is shown below. And and is shown. I'm sorry. And it also has a half-life of 5,730 years. So imagine, tagal. So nahahati siya after 5,730 years. So same, no? The activity of a sample is directly proportional to the amount of carbon 14. So we can write ln a sub 0 or the initial activity over the final activity, which is equal to kT. Okay. So let's try to answer the example. So we have here a tiny piece of paper taken from the Dead Sea Scrolls believed to date back to the 1st century or AD. And it was found to have an activity per gram of carbon of 12.1 atoms per minute, taking a or initial activity a sub 0 to be 15.3 atoms per minute. Estimate the age of the scroll. So we are given automatic half-life, no? Constant naman yung half-life natin ng carbon 14, which is 5,730 years. Okay. And we have uh, initial activity, which is A sub 0. It is 15.3 atoms per minute. Okay. So, and we have an equation which is T1 half or half-life is equal to ln 2 over K. Right? So, makukuha na natin yung K dito. Alright? So, we have here K is equal to ln 2 over, which is the T1 half, no? 5,730 years. So, our K or rate constant is 1.21 times 10 raised to negative 4 per year. Alright? Okay, so we will gonna use no this equation is equal to KT. So ang question was estimate the age of the scroll. So this is the unknown. So we already have the K. We already also have the initial activity. Okay, and we also have um, the estimated activity at present time and given. Di ko lang naisulat. We have A is equal to 12.1 atoms per minute. So, there, yeah, pwede na natin siyang ma-compute. So, we have ln A sub 0, which is 15.3 atoms per minute over 12.1. Remember, given na naman ito. Is equal to K. Our K is this one, 1.21 10 raised to negative 4 per year. So, multiplied by time t. So therefore, our time t is 1.94 times 10 raised to 3 years. So this is the final answer. So that is the age of the squirrels.